This is an introduction to Module 6, and in this module we'll be studying sections 4.3 and 4.4 in the textbook, in which we will begin to solve higher order linear differential equations. The first type that we'll concentrate on is the homogeneous linear differential equation, and then we'll be looking at non-homogeneous differential equations. The main thing about both of these is that they will have constant coefficients. The methods that we'll learn are only applicable for these equations when they have constant coefficients. So here's an example of a linear homogeneous initial value problem. So initial value problem, because we have some initial conditions right here. It is linear, as we can see, is homogeneous because there are no terms that are not multiplied times y or one of its derivatives. And as you can see, a1 through an, those are all real numbers. So I want to begin with having some intuition about these problems. So if we have an equation y prime equals y, then we want to find a solution. We have to think, what is a function for which its derivative is the same function itself? And maybe you given a little bit of time, you probably quickly think of y equals e to the x. It solves that differential equation because y prime is also e to the x. Now I could also have a constant, say a, y prime equals ay, and in this case also I could solve it with an exponential. It would be y equals e to the ax. So what we see is that we've pretty well looked at what solution to a first order homogeneous linear differential equation might be, and it is involving a exponential. So when we go into a second order linear differential equation, we're going to go ahead and make a guess that the solution is going to be also an exponential, and we'll take some number m and we're just going to see if this will solve the differential equation. We take the derivatives, y prime and y double prime, and then we're going to substitute all that into the differential equation and see if it can solve it. So you can see here that I've substituted, and this is my y double prime here, this is my y prime here, so b times y prime plus c times y. In solving this equation, I can factor out e to the mx, and then I'm left with this product of two functions equaling 0. Well, we know that e to the mx cannot be 0, so then this means that am squared plus bm plus c must be 0. And this that we've arrived to is what we're going to call the auxiliary equation. Now, we don't always have to go through that derivation to get to it. In fact, we can write it for a second order. As you can see, we have m to the power of the number of derivatives, so m squared, m to the power of the number of derivatives, so m to the 1, and then c times m to the 0 derivatives, or m to the 0, which is 1. So I'm going to replace my y double prime with m squared, my y prime with m, and my y with just the number 1. And then all I have to do is solve this quadratic equation in order to find the solutions to my differential equation. When I'm solving this quadratic, I will have, there will be three options, three things that could happen. One of them is that I get two roots, say m1 and m2, and in that case I'm going to be able to write the general solution to be y equals c1 e to the m1x plus c2 e to the m2x, as you can see here. If I have one repeated root, so say that the quadratic equation comes up to m minus 5 times m minus 5, then m equals 5 is the only value that I arrive to, then I'm going to be able to use the methods from section 4.2 to find a second solution, as you can see right here, and use e to the mx as my first solution. Now finally, when it comes to complex roots, which means that we had a negative under the radical, now here alpha and beta are just numbers, so you can imagine 2 plus I, 2 minus I, right? So in that case, alpha is 2, beta is 1. Then I'm going to be able to write a real solution in this form. And I want to refer you to pages 134 to 135 to read about how we come about to this real solution for the complex roots that appear in the quadratic. And we can continue with this method and go on and solve some third order and fourth order. It's just a matter of kind of repeating the same methods over and over again.